So we are looking at the phase equilibrium problem, phase equilibrium problem in multi-phase, multi-component, non-reacting, right? Multi-phase, multi-component, and non-reacting systems. Non-reacting means there is no reaction, right? There is no reaction between phases. There will be no new phase formed as a result of reaction. So if it is not so, but you have say multiple phases. Say for example, you have two phases, alpha and beta, and each of these phases are formed by say several components. So several components form these phases, and these phases are in equilibrium. Then part of the phase equilibrium conditions. If you remember, when we looked at this composite subsystem problem, where you had this composite subsystem, and then this was basically isolated composite system, and so you had, say for example, you will draw it properly. So if you look at that, you remember this. You had basically a isolated composite system. So why composite? Because you are having basically several subsystems here. So for add separated by a partition or a wall. So this we call wall. This we basically call as wall. And then we had defined, say for example, alpha subsystem and beta subsystem. We also told alpha is characterized by say something like U alpha, B alpha, then in A alpha, in B alpha, and so on. Similarly, you had U beta, V beta, then Na beta, and Nb beta. Now, instead of UVN type of a description, and then we told that S is a function of UVN, right? And we told that you had ds has to be equal to 0, right? So that's how we basically would solve this problem, and we made the wall. So basically we remove constraints from the wall. So what are the constraints? So for example, we removed constraints such as, we made it diathermal, right? It was adiabatic constraint. Adiabatic means no heat transfer. You remove that constraint and you allowed heat transfer, right? You made it diathermal. You made it flexible or basically movable. So basically the volumes can be exchanged. And then you also made the walls. So this was basically, it was made flexible. It was made diathermal, and also it was made permeable. So initially it was impermeable, then it was made permeable. And in the absence of all these internal constraints, we looked at how the equilibrium conditions will be arrived at, right? What will be the phase equilibrium conditions, or what will be the equilibrium conditions that will be arrived at by making sure that so S is a function of UV and N, then extremizing the entropy or maximizing the entropy. And basically, when you maximize the entropy, we found out what are the properties assumed, right? For example, we found some equilibrium conditions like its temperature of alpha, T alpha should be equal to T beta. Similarly, P alpha should be equal to P beta. And chemical potential of each component in the alpha phase should be equal to the chemical potential of each component in the beta phase, right? So the same thing you can do. Instead of using this condition UVN, as you know, we can now consider a system. Now we can consider the same system in contact with the surrounding. So basically you have a surrounding now. Right, we have a surrounding now. And the surrounding is nothing but a reservoir of temperature and pressure. That means a thermal and mechanical reservoir, right? So you have basically properties like TR and PR. Okay, alpha and beta are both in equilibrium with that. And then initially, so basically before any exchange happened, so you had, say for example, T alpha and P alpha, and you had composition, like say for example, in terms of mole fraction, I am talking about x2 alpha, x3 alpha, and so on. And then here you had P beta, P beta, and then you had x2 beta and x3 beta, and so on. And now basically you are describing this with the free energy. So if you are using G as a function of order G, if you write G, then you don't write you write T comma P, and then if you write Gm, say molar free energy, then you are telling that okay, you have x2 alpha, x3 alpha, and so on, right? So this Gm you are writing for the alpha phase and also for the beta phase. And then when you look at the equilibrium is basically the same. The equilibrium basically you arrive at is the same, that T alpha equals to T beta, P alpha equals to P beta, mu1 alpha equals to mu1 beta, mu2 alpha equals to mu2 beta, mu3 alpha equals to mu3 beta, and so on, right? So when you look at the equilibrium that you arrived at, the equilibrium, the equilibrium conditions like thermal equilibrium, mechanical equilibrium. So T alpha equals to T beta, for example, is thermal equilibrium. T alpha equals to T beta is mechanical equilibrium. And this for each component, the chemical potential, the equality of chemical potentials is basically chemical equilibrium. So you are looking at the same types of equilibriums here, right? So basically when we look at phase equilibrium in multi-phase, multi-component, non-reacting systems, we are looking at the total free energy to be minimized, and the total Gibbs free energy is a function of temperature, pressure, and the mole number of components in each phase. And we are again assuming that there is a phase boundary, and this phase boundary, so you have this phase boundary, and across this phase boundary there can be, so this phase boundary you can have these different components like 2, 3, and 4, they can diffuse across the phase boundary. They're permeable. So this boundary is permeable to the diffusion of these components. So it is permeable to the diffusion of these components, right? So for example, 1 can diffuse this way, 2 can diffuse this way, 3 can diffuse, means anyway. So basically from higher chemical potential to lower chemical potential, they will diffuse until the driving force becomes 0 and you achieve these equilibrium conditions, right? You achieve this equilibrium conditions like mu1 alpha equals to mu beta, mu2 alpha equals to mu beta, mu3 alpha equals to mu3 beta. So basically the exact same phase equilibrium that we arrived at with this concept of composite system with subsystems separated by a wall and basically removing internal constants from the wall is exactly applicable here, right? And you when get into these types of equilibrium conditions, right? This equilibrium condition is called thermal equilibrium. So if you have several phases, we have also done it as demonstrated for several phases, like you have like say for example you have alpha phase and then beta phase and then gamma phase. Now if you have several phases and each phase contains several components, across these you will have T alpha equals to T beta equals to T gamma, P alpha equals to P beta equals to P gamma, which is mechanical equilibrium. Again you will have mu1 alpha equals to mu1 beta equals to mu1 gamma if these phases are in equilibrium, correct? So basically, as I am telling you, so all this chemical potential equality are basically chemical equilibrium conditions. So chemical equilibrium, mechanical equilibrium, and thermal equilibrium are the three major equilibria that we will look at. And these equilibria we have already arrived at, right, using this concept of isolated composite system containing several subsystems that are separated by walls, and in the walls you basically imposed constraints, and then you started removing the constraints, and in the absence of all these internal constraints, the values attended by each subsystem, right, the values of temperatures or values of pressures attended by each subsystem or the chemical potentials are basically define the equilibrium, because that maximize the total entropy of the system or you can tell that it minimizes the Gibbs free energy of the system, considering that instead of considering instead of an isolated system, if we tell that overall composite system is in contact with the thermal and mechanical reservoir, right? So basically, we are looking at now Gibbs free energy minimization when the system is in contact with a surrounding which is nothing but a infinite thermal and mechanical reservoir. So in such cases, we basically use something called Gibbs free energy, and we look at Gibbs free energy minimization. When we look at total Gibbs free energy minimization, ultimately what we are looking at is dg equals to 0 and d2g is greater than 0. So that's what we are looking at, and g is a function of like g alpha and g beta, right? There is a total, so basically it's a function of all the, so it's a summation. G is the extensive property here, right? Unlike gm, so g extensive property is a summation of g alpha, g beta, g gamma, and g alpha, g beta, g gamma again are extensive properties, but although these are extensive properties, g alpha, g beta can be basically written as t alpha, a function of temperature, pressure, right? Instead of looking at S, right, entropy, we are looking at the conjugate. So we are looking at temperature, pressure, and also the mole number of different components, right? Mole numbers of components, right? So basically, we are looking at this condition where Pg equal to 0 and d2g greater than 0. In this case, we are telling that the system, the overall system, is in contact with the temperature and pressure reservoir or thermal and mechanical reservoir, right? So the idea is the same, and we are looking at the same equilibrium. We arrive at the same equilibrium conditions between phases. That is, between phases, if heat transfer is allowed, you will have P alpha equal to P beta. If volume change, if volume redistribution is allowed, that is the phase boundary is allowed to move, then you will have P alpha equals to P beta, right, at equilibrium, which is called mechanical equilibrium. And obviously, if diffusion is allowed, if diffusion across the phase boundary is allowed, so basically for components 1, 2, 3 and so on, you will have mu1 alpha equals to mu1 beta at equilibrium, mu2 alpha equals to mu2 beta at equilibrium, mu c alpha equal to mu c beta at equilibrium. Basically, you have achieved diffusional equilibrium. So diffusion will happen as long as mu1 in alpha is greater than mu1 in beta, or otherwise like mu1 in alpha is less than mu1 in beta. So basically, one can move either from one will always move from, the component 1 will always move from higher potential to lower potential, means chemical potential. Similarly for component 2 and component C. So basically, it will move unless the driving force goes to 0. That means the driving force which is given by the chemical potential difference goes to 0. That means that the chemical potentials of components in each phase, becomes equal, right? And that is called chemical equilibrium, right? So basically, if you have alpha, beta, gamma, and up to phase P, then you have also seen this, right? T alpha equals T beta equals T gamma up to Tp, which is equal to T equilibrium. Say for example, this is equal to T equilibrium, and for pressure, so basically this T equilibrium or P equilibrium is that of the reservoir, right? These are basically the temperatures, and see, all of the subsystems will assume the temperature of the reservoir, right? So basically at equilibrium, right? So you have T alpha equals to T beta equals T gamma up to Tp, P alpha to Tp, right? Because we have phase P also. So again, for each component, you have this chemical potential in for component 1, chemical potential in alpha should be equal to chemical potential in beta, equal to chemical potential in gamma, up to chemical potential in P, right? Similarly for component 2 and up to component C, right? So basically, if you have that, then basically what you see, you can derive by looking at the number of unknowns, like looking at the number of unknowns. Say for example, that unknowns are like T alpha, T beta, so on, and then P alpha, P beta, and so on, and then you have like X2 alpha. Okay, that is the mole fraction of the equilibrium mole fraction or equilibrium composition of component 2 in the alpha phase, then equilibrium composition of component 3 in the beta, component 3 in the alpha phase, and say 4 in the alpha phase, and so on. Similarly, the same equilibrium of component 2 in beta, component 2 in So beta, component 3 in beta, component 4 in beta, and so on, right? And you are also looking at, so remember, we are not writing component 1 because we are assuming component 1 to be, the component 1 mole fraction is the dependent, component 1 is a dependent component. So because x1 plus x2 plus x3 plus x4 for each phase, so for example x1 alpha plus x2 alpha plus dot 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 plus xc alpha should be equal to 1. So now if I take component 1 to be dependent, then I can tell 2 to c, all these are independent, right? So basically you have c minus 1 variables in each phase. In each phase you have c minus 1 variables or c minus 1 composition variables, right, which are expressed in mole fraction, and then you have also the variables p and t, right? So basically you have c minus 1 plus 2 variables, right, for all the p phases, right? You have so basically now if you look at the number of variables minus number of equations, what you get is called degrees of freedom, and from which we have already derived, and we found out this gives phase rule, which is F equals to c minus p plus 2. Now when you have condensed phase, we are assuming the pressure to be fixed across all phases, right? It is fixed for the entire system, right? We do not really consider the pressure volume work because it's negligible for condensed phases like liquids and solids. So then our degrees of freedom, because we are not considering this set of equations at all, we are not considering these at all, and we are telling that there is a fixed pressure, then basically F becomes c minus p plus 1. C is the number of components, p is the number of phases, and you have plus 1, and these basically give you the degree of freedom, right? So that right now, if you want to look at phase stability map, right, you often want to look at a phase stability map, because this phase stability map, if you think that it's whether it is, see, if you have gas phase, you cannot use the condensed phase diagram. Now if you look at a very simple binary system, so you have binary system, that means you have two components, x1 plus x2 is equal to 1, and therefore for in any phase, so basically you are taking x2 as the independent, so basically x2 as the independent, right? So basically you are taking 2 as the independent component in each phase. Means their compositions of their component in each phase. That means the concentration of 2 is independent in each phase, then the concentration of 1. So basically if you look at say alpha phase, you have x1 alpha plus x2 alpha equal to 1, right? It's a binary system, but you are telling x2 alpha is your independent variable, so x1 alpha automatically becomes your dependent variable, right? Now if you have right, so basically if this is independent, if this is considered as independent variable, that's your choice completely, then this becomes a dependent variable. In a binary system, in a ternary system, you can have two independent variables. If you have quaternary system, you have three independent variables in each phase, right? Three independent concentration variables in each phase, but so in a quaternary system, but the fourth one, right, is basically dependent on the other three, right, on the three independent concentration variables, right? So now if you look at that, you have gas phase coexisting. So if you have a PTX diagram, you have a pressure axis, you have an x-axis, you have a concentration axis. So you have pressure axis, right here, you have concentration axis, right, it's increasing here from 0 to 1, x2 equal to 0 to x2 equal to 1, and you also have the temperature axis, and see, you have these phase boundaries, right, but it becomes very difficult and very complex to understand such three-dimensional phase diagrams, right? So we start making projections. So basically we start making projections. So basically we fix the pressure, and if we fix the pressure, then we have one cut that we will just take, right? We will take one cut of fixed pressure, and at fixed pressure we will basically look at the phases that coexist and the phase boundaries. So if you look at that, there is also this some phase coexistence. For example, like here it is alpha plus beta, here it is like beta plus something, beta plus liquid or something like that. So basically what I am trying to say is that in such a case, right, in the PTX diagram, again this f equal to c minus p plus 1 or if in this case the degrees of freedom relation, right, if you look at this, say for example, if you look at the alpha phase field, so you have the alpha phase field. So if you are taking any point, so in this phase field, you will see f equal to c is 2 minus you have 1 plus 2. Basically, you have 3 degrees of freedom, which is basically equal to 3, right? Degrees of freedom equal to 3. Now, if you look at the single phase field, you have a degree of freedom 3. That means this alpha phase field in this PTX diagram is represented as a volume, right? It is like a space. It is like alpha occupies some space, right? It has volume, and this in this volume, if you want to specify pressure, temperature, you can have to specify. You can specify all the three, right? Pressure, temperature, and composition. However, when you go to a phase boundary means alpha beta coexistence. Immediately you will see that it becomes the degrees of freedom reduces to 2, right? So if you go to a phase boundary where you have alpha / beta coexistence, then you see in this PTX diagram it will become 2 minus 2 plus 2, which is basically equal to 2. So the degrees of freedom has now reduced to 2, right? So now instead of pressure, temperature, composition phase diagram, which becomes very complex, we look at temperature composition phase diagram at a fixed pressure if you have only condensed phases, if you do not have the gas phase. If you have gas phase also, liquid phase also, as well as the solid phases, so you have the solid, liquid and gas phases, then you cannot get rid of pressure, right? You have to consider pressure. However, if you do not have gas phase and if you have only condensed phases to deal with, right? For example, solidification problem, you have a liquid and you have several solids of different crystal structure. They're basically liquid and solids, and you can have also different liquids as a composition of different liquids, right? So in such a case, you can basically assume the pressure to be fixed because the pressure volume work is basically negligible, right? So this is at a fixed pressure. Say for example, this is at a fixed pressure. It is now much more clear, right? The diagram is much more clear because it's in 2D, right? You have a temperature axis, like the y-axis is your temperature axis, and you have the composition axis. Again, you can make it temperature versus activity diagram, right? There are various ways you can look at phase stability maps, right? But one of the most convenient ways of looking at phase stability maps, particularly in condensed systems where you have liquid phases and solid phases, is basically looking at these TX maps. And these TX maps at a fixed pressure, they're called basically phase diagrams. And these phase diagrams can be compiled experimentally, and then they can be calculated also using some computational techniques, and that computational procedure is called CalFAD. Okay, calculation of phase diagrams from from the available thermochemical data which is stored in databases, right? So for various alloy systems or various oxides or various high temperature materials and stuff, right? So you have a typical phase diagram here. Now, if you look at this phase diagram, if I look at fixed pressure, then basically we are looking at a Gibbs rule, which is F equal to C minus P plus 1. Now, if you look at the diagram, you have two components. So this is called a binary. So this is a binary phase diagram. Binary means the binary components, right? You have two components. Component 1 and component 2. Now component 1 has a x2. Now x2 is your independent variable. So for when you have pure component 1, x2 is going to be 0. Right? If you have pure component 2, then x2 is basically going to be 1. Now if you look at that, you have different regions, right? If you look at alpha region, say for example, and I am taking some point here in the alpha region. So basically, if I apply this phase rule at the alpha region, I get this 2 minus 1 plus 1, which is basically 2. So degrees of freedom I find is 2. Why is that so? Because if I am specifying a point, I am basically specifying temperature as well as composition, right? So basically when I fix a point, I have temperature here, right? We are reading it from the y-axis and we can now read it from the read the composition from the x-axis. However, now I can also have say alpha phase field, and here there is a beta phase field, and here it is alpha plus beta coexistence. Now if there is coexistence, that means there is some equilibrium, right? So now if I look at a phase boundary where alpha and beta coexist, for example, the degrees of freedom has changed. Here also the degrees of freedom remain the same. Again, you go to the beta phase region, it becomes different. Now 2 basically, so in a two-dimensional diagram, 2 basically represents also an area, right? So basically if the degrees of freedom are 2, then the region is represented by an area, like alpha or liquid or beta. If you look at alpha, single phase alpha, this is basically an area. A single phase beta is an area. Single phase liquid is an area. Now, if you look at these phase boundaries, they are now coexistence boundaries, right? They have like coexistence of two solids or coexistence of a liquid in the solid, for example. Now, if you have that, right? For example, this boundary is the coexistence between alpha and liquid, right? Now, in the coexistence region, you have F. In the coexistence region, you have F, which is C, is 2 minus 2, right? You have plus 1. So, basically, in the coexistence region, if I specify composition, my temperature is already fixed, or so on. If I specify temperature, then my compositions at equilibrium are already fixed, right? So, for example, if I specify temperature T1, now see I have drawn this dotted line here, so you can see at T1 this composition of the alpha phase that you can write here. So this is basically like X2 alpha equilibrium, and this composition at this temperature, this composition is another phase boundary, right? Alpha plus beta phase boundary here. So this X2 beta equilibrium, these are basically the equilibrium compositions of the coexisting phases, like the alpha phase and the beta phase. Similarly, you have, so this line that we draw here is called a tie line, right? And you can basically at that, so basically if you have certain alloy compositions, say for example certain alloy composition here, say I have an alloy composition here, then I can tell for this alloy composition what is the amount of beta phase I have and what is the amount of alpha phase that I have. But remember, whatever be the composition within the two phase region, you have a degrees of freedom which is basically equal to 1, right? It's basically equal to 1. So that means if I fix temperature, I already know the equilibrium compositions of alpha phase that is in equilibrium with the beta phase, right? So this is basically read by these points, right? These points here. So these points, so for example, temperature T1, this is the point and this is the point. These points represent the composition of alpha phase that is in equilibrium with the beta phase, and this point represents composition of the beta phase that is in equilibrium with the alpha phase at temperature T, right? At temperature T1, this is the composition and this is the composition that is equal. That means at this temperature T1, you basically are solving, say for example, mu1 alpha equals to mu1 beta, and you are solving also mu2 alpha equals to mu2 beta, and these two, the solutions of these two equations. So basically, if I have these two equations at temperature T1, like mu2 alpha equals to mu2 beta, and mu1 alpha equals to mu1 beta, then basically I get X2 alpha equilibrium, where we are looking at the alpha beta equilibrium, and we also get another thing, X2 beta equilibrium, which then we are looking at beta 5. Now remember, now this is something that you have to be very careful. If I know X2 alpha and if I know X2 beta, then basically X1 alpha equilibrium is nothing but 1 minus X2 alpha, right? So you have two, so you have So basically, you have seen at a fixed temperature T1, you have these two equations, right? Because pressure is anyway fixed. So at a fixed temperature T1, you have these two equations, and these two equations, these two variables, right? These are the two variables, and solution basically gives me the values of these variables, right? These are the values, right? These are the values. These are the values means I'm telling these are the points, and corresponding to these points, you drop a vertical line, exactly vertical line, and these points in the x-axis basically give you the equilibrium compositions of alpha and beta at temperature T1. Similarly, if I go to temperature T2, so for example, I go to temperature T2, so let's say this is temperature T2, then again I have this tie line, this horizontal line in the two-phase region, and again the ends of the tie line, that where it meets the phase boundary, these 2 points basically give me the equilibrium, right? The equilibrium between alpha and beta, or the equilibrium compositions of alpha and beta, right, at temperature T, right? So that is what it gives me, right? Also, additionally, if you know the alloy composition in a two-phase region, to give me what is the phase fraction, what is the amount of alpha phase, what is the amount of beta phase, right? That is also something gives me. Similarly, for example, here you have another tie line in the liquid plus alpha region. So here the equilibrium is between alpha and liquid, right? This is something that you often see when you are basically, say for example, often you have to solve such problem when you are looking at, say for example, a process where liquid is cooled, and then once the liquid is cooled, the liquid is solidifying, and as the liquid is solidifying, you are forming this alpha nucleus, and these alphas are growing inside, and as they are growing inside, the composition of the liquid is also changing, right? Because say for example, when I am here, when I am exactly here, then basically you have just started nucleating some alpha phase, right, of this composition, right? You are here, but the fraction of alpha phase is almost negligible. It's very, very small. It's at the nucleation stage. Now you go cool further, then you basically, so as you are cooling further, you are basically seeing the solid is enriching in solid, right? The solid is picking up. So basically, if you look at it, if you look at the cooling curve, you are seeing that the solid basically now becomes richer in X2, and liquid basically is now, so liquid was here, and now solid is also rejecting some amount of solid, right, when it is solidifying, right? So basically, as you go down, you see the liquid and solid compositions are changing, right? So here what is happening, so you are going, so this side it is like leaner in B, this is richer in B, and as you go further, you are getting richer and richer in B, right? So you are getting an alpha which is much different than the alpha that you got when you first solidified. So alpha composition here and the alpha composition here are vastly different. In here, alpha contains less solute B, or the component 2. So alpha at this composition has less of 2 than at this composition. At this composition, you have more 2 here, and also if you look at that, at this composition, the liquid also, say for example, this is the solid composition, and the liquid composition also has also a lot more solid. So you are basically rejecting that as solidification progresses, right? As solidification progresses, you are basically seeing seeing a liquid that is richer in solid, right? It is rejecting. So basically, as it solidifies, it rejects solid, but it also picks it up, right? You can see on this curve, right? So that's the idea. So this is the solidus. So solidus, basically this curve is called solidus. The solidus separates the single phase from the liquid plus alpha coexistence, and the single solid phase alpha from the liquid plus alpha coexistence. So this is called solidus, and this guy is basically called liquidus, right? This guy is called liquidus, and you can see this is basically a very interesting diagram. So you have one particular temperature. If you look at that, so I'm just giving you some characteristics. I will go through each of these details, but you will see that there is one very special temperature, a very special temperature at which, so this is like say T, let's call it T, is a special temperature at which if you go to one point like this, if I go to one point like this, right, at this temperature. Remember, we are going exactly at this temperature. This temperature, you see a very interesting thing. You see at these points, for example, at this point or at this point, or in fact at this point or this point, you see that there is a beta phase, there is alpha L phase, and there is alpha phase. There are three phases coexisting. So F at this TP, at TP, along the line, right, at TP, obviously not here, not here, but as soon as you go along this line, say let's call this line, say some PQ line. If you go along this PQ line, any point in the PQ line will have F, which is equals to 2 components minus 3 phase coexistence plus 1, 2 minus 3 plus 1 is equal to 0. So basically, these points are invariant points. These points are such that once you have this point, at this point 3 phases coexist, and at this point you cannot specify anything. You cannot specify the temperature or composition. Everything is automatically fixed, right? So basically, here the degrees of freedom basically becomes 0, right? So if you see within the two-phase region, and also at the phase boundaries, degrees of freedom become 1, right? It reduces. In the single-phase region, you have degrees of freedom 2, and in the three-phase region for a binary system, you have degrees of freedom 0. So it means that is like an invariant reaction that you are looking at. And any point on this basically is fixed. The composition, temperature, everything is fixed, right? So that is called basically the invariant points. These are the invariant points in a binary system. The degrees of freedom basically go to 0. Now we look at different types of phase diagrams. So one of the phase diagrams that we can think of is like, right, is like you have this binary alloy B. So I am basically concentrating currently. So if you look at, you can in principle look at ternary phase diagrams. So you can look at ternary phase diagrams. I will not discuss ternary phase diagrams here. Okay, if later time permits, then we will give 1 or 2 examples. So in ternary phase diagrams, as you can see, even if pressure is fixed, so P is fixed, then also you have 2 independent compositions, right? So basically what you do is basically construct a triangle, okay, which is called basically a Gibbs triangle. So this is an equilateral triangle. So instead of the isosceles one that we have drawn here, so you have this Gibbs triangle. So where in this Gibbs triangle you have like one A, this is pure A, this is pure BN, and this is pure CN. But if you see, you have now, say for example, if I tell from B to C, this is your, so XB and XC, right? Basically now this is from C to A and C to B, right? So now if I tell XB to be one variable, so XB to be one variable, so if I am looking at that, and we are looking at XC, so basically XA plus XB plus XC equal to 1, right, for any phase. So if you have several phases coexisting, then if you see, you have only composition here, right? You have composition here. So I can draw a simpler diagram. So basically you have this type of a diagram, this type of a composition axis, but where is the temperature axis? The temperature axis, if you have to draw, then again you have to look at a 3D picture, right? You have to look at a 3D picture, right? So you are looking at a 3-dimensional picture because temperature is going this way, right? You are looking at a 3-dimensional picture, right? So basically now you are saying that there are these phases, and these phases are coming inside and coming inside. Say for example, you have like another thing coming inside. So it becomes very complex, right? It becomes very complex to understand. So what you do, again in ternary phase diagrams, you look at projections, right? What are the projections that you look at? Often look at 2 types of projections. One is called isothermal projection, that is at a given temperature. This is called an isothermal projection that you map on the Gibbs triangle, that equilateral triangle that we have drawn. So these are called isothermal projection. I will come to this later. And then there is also something called vertical section or isoplete. Okay, so vertical section which looks similar to a binary phase diagram, but with lot of differences, right? With lot of differences. You do not really obey any of these rules there when you are looking at a section, right? So basically, these are things that, these are the nuances that you have in ternary phase diagram, and if you are basically very interested in ternary phase diagrams, then you can look at the book by Alan Prince on alloy phase equilibrium, which is available now. Basically, this is a classic book. This book is now available online, I think by MSI Port. MSI Port has given you this alloy phase equilibrium book for free. It's a wonderful book on phase diagrams, and particularly if you are looking at or interested in ternary phase diagrams. Okay, that was the points. Now the idea is that if you go there, now let us look at binary alloy diagrams, and we are looking at it in a more intense and systematic way. So we will look at this binary alloy AB. So if we understand binary alloy phase diagrams, it will be also, so the knowledge basically can be applied to ternary diagrams, and you can or you can look at, say, some quaternary systems, where again you can look at some pseudo binary or quasi binary sections, and you can basically make sense of this, right? So you have like this binary alloy AB, and you have, and in these type of phase diagrams, so we call it type 1, and in these type of phase diagrams, the components have infinite solubility in the liquid state but zero solubility in the solid state. So infinite solubility in the liquid state and zero solubility in the solid state. So basically, the infinite solubility in the liquid state or liquid phase, and we assume that the liquid phase is an ideal solution. Now, if it's an ideal solution, as you know from Raoult's law, the activity of A in the liquid phase is equal to the mole fraction of A in the liquid phase. Even activity of B in the liquid phase is equal to mole fraction of B in the liquid phase. Now, as you know that when that is so, then for in each phase, in the liquid phase, for example, mu A is 0. Mu A 0 is the chemical potential of A in the standard state, right? Or the standard state can be pure A, right? For example, pure A solvent, right? If you think of a pure A solvent, the standard state is given by mu A 0, right? So this is basically for mu A 0, and this is the chemical potential of A in solution. So chemical potential of A, component A in the solution is equal to component A in pure state or of that of pure solvent plus RT ln, right? That is what is the definition, right? That's what we have seen so far, right? You have a solution. In a solution, basically you have now A and B both. So basically it deviates from mu is 0, right? And we have looked at this like delta mu A equals to mu A minus mu is 0. Now if I look at delta mu A, if I look at delta mu A, then what will I write? Delta mu A, which is basically mu A solution minus mu A 0, which is standard state, which comes out to be RT ln, right? This is delta mu. For delta mu B, it will be RT ln x, right? Now you are looking at, say, for example, the liquid to solid transformation of pure A, right? You are looking at, say, liquid to solid transformation of pure A, and then let us call that liquid to solid transformation of pure A is given by this temperature, which is called, for pure A, this is the freezing point, and it is given by TA comma freeze in the A comma freeze in the subscript and 0 in the superscript, right? So basically this is, so 0 in the superscript basically points to pure A solvent, and is telling me this entire guy is basically freezing point of pure A solvent, right? Now if I look at delta mu is 0, now delta mu is 0, say for example, when you are looking at pure A and you are looking at liquid to solid transformation, then delta mu is 0 is equal to 0 equals to delta is equal to, now at the TA0 freeze, the delta mu is 0, that is the relative partial molar quantity, or basically the chemical potential difference between A in the solid state and A in the liquid state. So A in the solid state is given by AS subscript, A in liquid state is given by AL subscript, and 0 indicates pure or 0 indicates standard, right? So mu A 0 AS minus mu 0 AL. So basically mu is 0 A in the solid state mu 0 A in the liquid state. So this is the difference. Mu 0. So basically, since the solid and liquid are at equilibrium at TA0 freeze, right? This is the freezing point. At the freezing point, since the solid and the liquid A are in equilibrium, you can tell mu A is 0. A is 0 basically means this is pure solvent in the solid state. And this is pure solvent in the liquid state. Now, this minus this has to be equal to 0. Why? Because mu A in solid is equal to mu A in liquid, right? In the pure state. Right? It has to be at E equals to TA naught, right? Because it's the freezing point of TA, right? TA naught. Right? So basically, what we are telling is that chemical potential difference between the solid and the liquid at the freezing point, the pure solvent has to be 0, right? Now, if I look at now solution of A and B, then if I now in that solution, if you are now looking at mu AS and mu AL, so at TA0 freeze, so if you are looking at mu AS and mu AL, but if you are looking at, so when you have a solution of A and B, then basically mu A is 0 and mu A is 0. The difference between the chemical potential of pure A, right, in the solution. So chemical potential of pure A in the solution, in the solid state is minus the mu Al 0, the liquid state. That is not going to be equal to 0, right? That is not really equal. But what is equal is in the solution of A plus B. Let us assume there is a, so why it is not equal? Because TA0 freeze is no longer the freezing point. As soon as you have a solution of A and B, as soon as B solute is entering the solution, then TA0 freeze is no longer the freezing point of the solution. The freezing point is different. Now, they are different. Now, as you can see, that solid-liquid coexistence, okay, even if we think of the pure state, means we are looking at pure A, the solid-liquid coexistence, because it is not really pure A, you have a little amount of solute here. So, you basically see this mu S and mu Al are no longer equal to 0 at this temperature, right? So, but if you look at mu S, so basically you can get rid of these zeros here, because zeros assume pure state. But what I am telling is mu S minus mu Al at TA0 freeze, right? Because for solution of A and B, freezing point is different. Freezing point is not equal to TA0 freeze. TA0 freeze is the freezing point of the pure solvent A, right? But at TA0 freeze, if you have a solution, then mu AS, which is the chemical potential of A in the solid state and in the solid phase, and mu AL, which is the chemical potential of A in the liquid phase, at this temperature TA0 freeze, because this is no longer a freezing point, at this temperature they are not equal, right? They are not equal. So the difference between them, right? They are not equal, right? As you can see, not equal. So if you look at that, so what we are telling now is like delta mu, that is the difference. There is a finite delta mu. Delta mu can be positive, the delta mu can be negative, but the point is, because it depends on what is the new freezing point, whether the freezing point is depression, whether the freezing point is basically elevated, right? We do not know. So if I look at a solution of A and B, if we define a new freezing point, which is T freeze, then we can now tell delta mu A, that is the relative partial molar free energy, or the chemical potential of A, right, in the solution, the difference in chemical potential of A in the solid, chemical potential of A in the solid and that in the liquid, right? So basically the difference between the chemical potential of A in the solid and mu Al, that is that in the liquid, is equal to 0 at T freeze, because at T freeze again you have T freeze, the solution freezes, right? Solution freezes means there is a, so at T freeze you have an equilibrium between the solution in the solid state and solution in the liquid state, Now, if that is so, then delta mu A, which is the relative partial molar free energy of component A, which is basically equal to the difference between the chemical potential of component A in the solid state and then chemical potential of component A in the liquid state. So basically, for each component, as you remember from equilibrium, you will have for each component at the T freeze, right, at the equilibrium temperature T freeze, right, for the solution. So at T freeze, which is the equilibrium temperature, solid equilibrium temperature means at T freeze, solid and liquid will coexist, right? Solid solution and liquid solution coexist, right? So in such a case, you will have mu AS should be equals to mu L, right? Often you would also write this way: mu A in the solid is have to be equal to the mu A in the liquid, right? Just for convenience, I have put mu AS and mu AL. Sometimes in books they also put this way. This practice mu AS and this is mu, right? You can write this way, but I have gotten rid of the bracket. I have just written this as AS here and A liquid here. So the bracket is already in place, right? Now you have this Gibbs-Helmholtz equation. Okay, this Gibbs-Helmholtz equation, or this Gibbs, which basically you can prove, and you will see that it is basically del G by T del T, that is the partial derivative of G by T, G normalized with temperature with respect to, so partial derivative of this quantity, okay, with respect to temperature, keeping pressure and the mole number of components constant, is equal to minus H by T square, right, minus H by T square. So similarly, so basically mu AL, so mu AL is the partial molar free energy of A in liquid, right? Partial molar free energy of component A in liquid divided by, so partial molar free energy is also with the same equation. So if you have partial molar free energy of A in liquid by T, and you are taking this partial derivative with respect to temperature, taking pressure and the components, the concentration of components fixed, that is equals to, again based on the Gibbs-Helmholtz relation, it is equals to minus H bar AL. So basically it is H bar A. H bar A is the partial molar enthalpy of component A in the liquid. So AL basically means A in the liquid state, right? Partial molar the partial molar enthalpy of component A in the liquid state by T square. But this is also equals to minus HA0 by T square. Why? Because as you know, since in ideal solutions, or if it's an ideal solution, right, we are talking about ideal solution, then the change in enthalpy, change in partial molar enthalpy for component A, right, the change in partial molar enthalpy of component A, the change is here. What we are looking at, if we are looking at, this is in the liquid solution, right, this is in the liquid solution, and this is in the, so 0 basically means it is a pure state, right? So so it is like after mixing, and this is before mixing. So this is the after mixing enthalpy minus the before mixing enthalpy, or delta HAL. This is nothing but it's basically like partial molar enthalpy of mixing of component A. Partial molar enthalpy of mixing of component A. As you know, the partial molar enthalpy or the molar enthalpy of mixing of the mixing basically for an ideal solution is equal to 0. So basically delta H bar AL, which is H bar AL, which is the partial molar enthalpy of component A in the liquid solution, minus partial molar enthalpy of, or molar enthalpy of component A in the pure state in the liquid. Basically, the difference between them is going to be 0 because you are assuming ideal solution, right? That we have already discussed. Similarly, for mu AS, we can write it is H bar A minus H bar AS by T square, which is basically minus H bar A 0 by T square, which basically means that at the partial molar enthalpy of component A in the solution by T square, then the partial molar component of enthalpy of, or molar enthalpy of component A in the pure state, they are basically going to be, the difference between them does not exist. They are going to be the same because delta H, basically the change in delta H, or means the delta H mix is basically 0, right? Delta H mix is 0 for ideal solutions, right? Whether it's an ideal solid solution or a ideal liquid solution, right? If you look at liquid to solid transformation, you see liquid to solid transformation is basically an exothermic transformation, right? It's an exothermic transformation. Exothermic means gives out latent heat, or it gives out heat of transformation, and that is called H, delta H0 freeze. Now, if it is giving out, that means delta H0 freeze is negative, which is basically negative of delta H0 melt, because melting process is a endothermic process, right? The solid has to absorb it to convert to liquid, right? So this delta H0 melt is nothing but, so this is from liquid, so basically delta H0 freeze is nothing but it is transforming from liquid to solid, right? It is transforming from liquid to solid. So this will be solid minus liquid. So final state is solid, right? Final is solid, and then so this is final. So this is in the 0th state. Remember, this is at 0. 0 means pure state. So you are looking at pure A, right? Pure A solid. The enthalpy of pure A solid, right? And enthalpy of pure A liquid is what we are looking at, and the difference between them is basically, so this is the liquid to solid transformation. So this is the final state, this is the initial state, right? This is final state, right? HA is 0, and right in a freezing experiment, this is the final state. The solid state is the final state, and this is the state that you start with, that is the liquid, right? And the liquid is freezing, and you get the difference, and this difference is basically nothing but delta H0 freeze, which is negative, of the delta H0. Delta H0 is basically positive, right? Now, if you look at that, now think of this. Now again you can apply for the relative partial partial molar free energy of A, or the difference in chemical potential of A when you go from liquid to solid. If you are looking at that, so that is basically given by del mu S by T del T, right? So del mu S by T del T, because you are looking at that, right? Mu A from L to S, the delta mu, right? Delta mu A, that is for component A from L to. So now it is basically partial molar free energy of component A in the solid. So that is what you have written here, or chemical potential of component A in the solid by T, and you have chemical potential of component A in the liquid by T del T, which is basically again given by if you look at that, you apply this relation, right? You have this relation minus HA0 by T square, here it is minus HA0 by T square. So this basically becomes minus HA0 minus HA0 by T square, which is minus delta H0 freeze by T square, right? So why R came? Why does the R come? Or is it, there is no R here. Currently there is no R, so we can remove the R here. So this basically becomes minus delta H0, because there is no R here. I don't see any R here. So basically this comes from again the Gibbs-Helmholtz relation. So this is nothing but delta minus of delta H0. So basically you are looking at liquid to solid transformation. So del delta mu A by T, that is the chemical potential of component A by T, and so this we will call as delta H0 freeze, right? Delta H0 freeze of component A. Remember, this is for component. This is, we are doing it for component. We can do it also for component, right? So now, if you are looking at that, if you are looking at this equation, so you can now integrate it, right? You have delta mu A at T0 freeze, right? Basically at delta mu at T0 freeze, and you have like delta mu at T freeze. Now you see the difference. The difference is that in one case you are looking at the relative changing of the potential of component A, which is in the solution, right? So if you look at this is the solution state, right? T freeze is the new freezing point of the solution, and this is at T0 freeze. And you are looking at d of delta mu A by T, right? So this is the d of delta mu A by T equals to minus delta H0 by freeze by T square. So delta H0 freeze by T square dt, right? So basically I am taking that. So delta H0 freeze, we are assuming that it does not change with temperature, and we have T0 freeze, which is the freezing point of the pure solvent, and T freeze, which is the freezing point of the solution. And you have now dt by T square. So basically you can write delta mu A T freeze by T freeze minus delta mu A 0 T0 freeze by T0 freeze, right? So basically equal to delta H0 freeze 1 by T freeze minus 1 by T0 freeze. Right? How does it come? dt by T square equals to minus 1 by T, and you are looking at T freeze here and T0 freeze here, and this minus sign, and there is a minus sign here, right? There is a minus sign here, and then there is another minus sign because of integration, so minus minus equals plus, so these terms and this term. But here, be very careful. If you look at that, this is delta mu a, and this is also, you can call it delta mu a only. So you have delta mu a at T0 freeze and delta mu at T freeze. Remember, these guys, delta mu at T freeze, is where you are looking at the chemical potential difference of components. So basically, you are looking at you are looking at chemical potential difference of component A between the solid state and the liquid state, or the liquid state and the solid state. Right? Liquid state is the initial state, and solid state is the final state. So it is basically solid minus liquid. So if you are looking at final minus initial, so delta mu at T freeze by T freeze, right? Because that's the thing, that delta mu at T freeze by T freeze is your one of the, so remember, this is not mu as 0. Don't put 0, because 0 means this A is in the pure solvent state. We are not looking at that. We are looking at delta mu A only. That is the delta mu A is the relative partial molar free energy of component A, or you can tell that it's the difference in chemical potential of component A. Of component A in between solid solution and liquid solution. Right? So that is the delta mu. So delta mu A is the difference. So I am not just keeping it here because it becomes clumsy. So what I am trying to say, delta mu A, as you have seen, delta mu A is basically mu A solid minus, this is what we are doing, mu A the liquid. I have given bracket, but we need not, so I am following this convention, mu A S minus mu A. Right? So basically I didn't give this bracket, so I just write this way. So this is basically, now this we are evaluating at two different temperatures. We are evaluating at T0 freeze also. T0 freeze is the freezing point of the pure solvent, and T freeze is the freezing point of the solution. Right? Now if you do this integration, I am removing this, and you assume that delta H0 freeze is not basically changed as a function between T0 freeze and T freeze, then basically delta H0 freeze can come out of the integration, and you have dt by T square. dt by T square is minus, so dt by T square, if you look at that, is minus T minus 2, right? T minus 2 plus 1 by minus 2 plus 1, and there is no minus sign here, right? T minus 2 plus 1, so basically this becomes equal to minus of 1 by T, and then, right, minus 1 by T, and then you take the limit of that, and there is a minus sign here and there is a minus sign here, that becomes plus. Okay, now, so you have delta mu at T freeze by T freeze, right? You are looking at this, right? Delta mu at T, right? So that one. So delta mu at T freeze by T freeze minus delta mu at T0 freeze by T0 freeze is basically delta H0 freeze 1 by T freeze minus 1 by T0 freeze. Now at T freeze, mu A at T freeze, the new freezing point, mu A S equals to mu A L, that is the, or delta mu A equal to 0. Excuse me. Right, at t freeze. But at t0 freeze, delta mu a is not equal to 0, right? So because delta mu a is 0 at t freeze, right? At t freeze, this is a very important balloon, right? I am just taking it as a balloon here. At t freeze, mu as equals to mu al, right? Because the mu as is basically the chemical potential of A in the solid state, and this is chemical potential of A in the liquid state or liquid phase. And if they are equal, right, at t freeze they are equal, because t freeze is the new freezing point. So at that freezing point, at the new freezing point of the solution, delta mu a is equal to 0. This is very important point here. So this guy goes to 0. So there is a minus delta mu a t0 freeze. Now delta mu a t0 freeze is not equal to 0, right? We have already told that, and we can also realize that, right? That mu as t0 freeze, mu as t0 freeze. Here right? So basically at the freezing point of pure A, right? Freezing point of pure A is no longer the freezing point of the solution, right? So at the freezing point of pure A, or which is basically, now I am just writing it as simply as t0 freeze, right? T0 freeze is the freezing point of the solution. So I wrote as Ta0. So basically, please note that T0 freeze is nothing but Ta0 freeze, right? It's a pure solvent, right? So T0 freeze is the freezing point of the pure solvent, right? At this temperature, the chemical potential of A in the solid, like mu S, is not equal to mu Al. So as a result, this guy does not go to 0, right? As a result, this guy, since mu A is not equal to mu Al at T0 freeze, therefore delta mu A is not equal to 0. So you have this term. So this term vanishes, while this term remains, right? So this term is remaining, which is equal to minus delta. So basically minus delta mu T0 freeze equals to delta A0 freeze 1 by T freeze minus 1 by T0 freeze. Now T0 freeze minus T freeze, let us call it as delta TFR. So basically it is like T0 freeze minus T freeze is the deviation, right? Which is the deviation or in the freezing point. It can be an elevation, it can be a depression, we do not know priori. So we are just telling T0 freeze minus T freeze is delta TFR. And we are telling that delta mu at T0 freeze is not equal to 0, right? Obviously. Now delta mu at T0 freeze is nothing but mu as T0 freeze minus mu Al T0 freeze, right? Now if you have that, and you now assume that mu as T0 freeze equals to mu as 0, that is the pure solvent in the solid state, right? T0 freeze plus R, and you have now T0 freeze RT ln, and you have X in this. So this is the composition of or mole fraction of component A in the solid solution, right? Mole fraction ln XAS, right, is in the solid solution. And you also have, and similarly for mu Al T0 freeze, we are writing mu Al T0 freeze, that is the freezing point of the solvent. But now we are looking at the solution, which is equal to mu Al0. Now mu Al0 means that is for the pure solvent, right? Mu Al0 T0 freeze, remember, right? Plus R T0 freeze and then X in the liquid state, right? And then XA is basically the composition of A or mole fraction of A in the liquid state, right? That's why XAL, right? You can also put XA, you can write this as XAL, okay? Or you can write this as XA and L, right? Whatever way you want to write, does not matter. So basically X. So this term, now you see, if you have that, If you expand these guys, this way, so mu as T0 freeze is this guy plus this guy, right? Mu as 0 plus RT0 freeze ln XAS, and again this one is minus, so mu L0 T0 freeze minus RT0 freeze ln XAL, right? This is XAS, this is XAL. Now if you look at that, XAS is basically the concentration of component A in mole fraction in the solid state, and XAL is concentration of component A in the liquid state, right, at this T0 freeze temperature, right? Now if you look at this, mu A0 T0 freeze and mu L0 T0 freeze are, right, this is because it is pure solvent, right? 0 means this is pure solvent. So for the pure solvent at T0 freeze is the freezing temperature. At this temperature, mu A0 is equal to mu L0. So you can basically cross them out, because this has to be equal to this one and this minus this has to be equal to 0. So these guys go up. Now if you have that, now you have only this term and this term remaining, right? So basically you have minus RT0 freeze ln XAS by XAL, right? Because you have this, right? RT0 by XAL by T0 freeze, right? Because you have by T0 freeze, right? If you look at this equation, it was still at by T0 freeze equals to delta I0 freeze 1 by T freeze minus 1 by T freeze 0. So basically if I write further, ln XAS by ln XAL is basically delta I0 freeze by R, and then there is a minus sign here, so this becomes minus sign, right? This minus sign comes here, so minus sign delta I0 freeze by R 1 by T freeze minus 1 by T0 freeze. Now since delta H freeze itself is basically negative of delta H0 melt, so I can write minus of delta H0 freeze is nothing but delta H0 melt, which is positive by R 1 by T freeze minus 1 by T 0, right? So that is exactly what we are looking at. If you do that, ln XAS by ln XAL, this can further be written as ln 1 minus XBS by 1 minus XBL, right? Because XAS plus XBS should be equal to 1, right? XA in solid state, in the solid, plus XB in the solid should be equal to 1. So that means XAS is 1 minus XBS and XAL is 1 minus XBL. Now this is like ln 1 minus XBS minus ln 1 minus XBL. Now basically if you think of this as a very dilute solution, like ideal dilute solution, that is the amount of B is very small, then ln 1 minus XBS can be written as minus XBS. And this can be written as minus XBL. However, there is a minus sign ahead, so it becomes plus XBL. So this becomes XBL 1 minus XBS by XBL. Now XBS by XBL, we can consider it as L, or we can often, here I am writing it as L, which is basically XBS by XBL is nothing. L is here the partition coefficient, right? If L, you can call it P also, right? You can call it P also, but here I have called it L, which is XBS by XBL, which is the partition coefficient of solid, between solid and liquid, right? So partition coefficient between solid and liquid solutions. So if that is so, we can do further the simplification, because ln XAS by XAL is this guy. So basically, if we do further simplification, you can write XBL 1 minus L is basically nothing but, right, because XBS is basically, so if I do look at this, why did this come? This comes because you have XBL, right? This is XBL 1 minus L, right? So basically, you are writing this guy, so this one that you have in this, this equation, this is now replaced by this guy, right? So this becomes XBL 1 minus L equals to delta H0 by R, delta T freezing by T0 freeze times T freeze. Now you are telling that T0 freeze and T freeze are very close, right? They are very close. Now if I tell T0 freeze and T freeze are pretty close, then we can approximate this, like T freeze and T0 freeze. The product can be approximated as T0 freeze square, right? So you have T0 freeze square, you have R, and you have 1 minus L XBL by delta H0 mel, right? Basically, you are looking at delta TFR basically as a function of all these parameters. Now this product we are calling as T0 freeze whole square, and you are taking this guy here, R goes up and you have this term. So basically delta TFR is this, right? So when L, now if you look at that, when L is less than 1, that is XBS by XBL is less than 1, that is XBS is less than the amount of B partitioning in solid is less than the amount of B partitioning in liquid, then in that case you have the delta TFR which is greater than 0, or T freeze is less than T naught freeze, which gives you depression, right? This gives you depression of freezing point, right? Which is in general the case, right? In general this is the case, right? There you will have depression of freezing point, right? When you put, this is a colligative property that we have learned for solutions, right? So basically depression of freezing point. When Al is less than 1, mind that when Al is less than 1, Al less than 1, you have XPS less than XPL, then in that case delta TFR is 0 and you have depression of freezing point. However, when Al is greater than 1, XBS is greater than XPL. That is the amount of solid. The partitioning is such that amount of B or amount of solid in the solid state is more than that in the liquid state. It's generally not really common, but it may happen. In such a case, delta T freezing will be less than 0, or T freeze, basically the freezing point of the solution, will be greater than the freezing point of pure A, right? So T0 freeze is that of pure A or pure solvent. So you are telling the freezing point of solution is now elevated, right? So there is an elevation. So this is basically leads to elevation of freezing point. Now, if you look at that, now if you see Q naught, I can go further. If you tell Q naught is the specific heat, right? Specific heat is in joule per gram, right? Specific heat of pure solvent A in joule per gram, then delta H0 mel, right? Delta H0 mel is nothing but 1000 QZ, right? Because it is joule per gram, and we are looking at delta H0 mel, and we can write it as if I look at 1000 grams, if you are looking at 1000 grams, basically 1000 grams. Why did I do 1000 grams? Because I want to look at per kg of the solvent, right? We are going to use molality. Molality is number of moles of B in 1000 grams or 1 kg of solvent A. So 1000 grams of A is nothing but 1000 by Ma. Ma is the atomic weight of the molecular weight or atomic weight of A. So 1000 by Ma moles of A. So you have 1000 by Ma moles of A. And for dilute solutions, XB, which is basically nothing but NB by Na plus NB, which is nothing but NB by Na, and you can write XB liquid, for example, is nothing but approximately MBL. MBL is the molality of B in the liquid state times Ma by 1000, right? You have 1000 by Ma here. You can easily put this, right? 1000 by Ma is contained is 1000 by Ma. Moles of A are contained in 1000 grams of the solvent. Now, if you do look at XBL, XBL, so because by using this definition, right, XBL is approximately equal to more MBL times Ma by 1000, right? You are neglecting B, the amount of B, right? So if that is so you have this equation, right? XBL, so MBL is the molality of solvent, and so if you look at that, Ma by 1000 is basically, Ma is the atomic weight or molecular weight of A, component A, right? A can be what? A can be some compound, right? So that's why I'm telling Ma is the molecular weight of A. But if it is not a compound, it's an atom, then it's basically it's a pure atomic species. Then basically this becomes an atomic weight. But you see, this is in grams, and then this is in mole, right? Ma is grams per mole, and you have 1000, and here you have MBL, which is moles per gram, right? 1000 grams. Moles per kg basically, or moles per 1000 grams. So basically gram cancels out, mole cancels out, and right? Basically mole cancels out, and you basically get XBL, right? XBL, which is mole by mole, right? Which is basically mole by mole, because mole by 1000 is basically MBL, right? So basically mole by mole, and therefore that is mole by mole is nothing but mole fraction, right? Moles of B in the liquid by total moles of total number of moles of the liquid, right? Total number of moles of liquid is basically NaL. So basically Na in liquid state plus Nb liquid state basically gives me N. Now you are telling NBl by NL, nothing but X, right? So if that is so, we can basically write, so this is just a convenience, so delta of TFR can be written as this, with this in terms of molality, right? And where Kf is R T0 free square by 1000 Q0. Q0 is the specific heat, right? Specific heat. So instead of looking at enthalpy of transformation, if we are not given enthalpy of transformation but we are given specific heat, that also suffices, right? Now if XBS equal to 0, now when does XBS go to 0? XBS goes to 0 when there is no solubility of B in the solution, right? By the way, when we are looking at the phase diagram, when we try to construct the phase diagram, we are assuming no solubility of B in the solution. So basically in such a case, L, which is XBS by XBL, will be equal to 0. So in that case, delta TFR, that is the change in freezing point, is nothing but this Kf, where Kf is R T0 free square by 1000 Q naught, where Q naught is the specific heat of pure, right, of the pure solvent. Now you have, which is proportional delta TFR, that is the change in freezing point, is equal to this Kf, which is this constant, times the molality of B in the liquid, right? Molality of B in the liquid. If you look at phase equilibrium, now you are looking at all the ranges, right? We are now basically, see, we did it for ideal dilute solution, but if I want to use the same equation, that is why I did all these derivations, to show you that we have done it for ideal dilute solution where B is like very small amount of B is present in A, right? So A is like a major solvent and you have minority solute. But instead of that, if you look at now phase equilibrium condition, where you are looking at like the complete composition range from pure A to pure B, right? When you are looking at phase equilibrium, you are looking at composition range from pure A to pure B, right? The entire composition. Now you are telling A plus B, and we have given this condition, A plus B completely soluble in liquid but no solubility in solid. So if I look at now ln XAS by XAL, we get this equation, right? Delta HA0 melt, that is the relative partial molar enthalpy of component A, right? And but there is a 0, so basically delta HA0 means this is basically the change in molar enthalpy of component A, of, right? So basically this is delta H melt only, right? So basically it's 0. So basically this is the transformation, the heat of transformation or heat of melting, okay, or latent heat of melting of pure solvent, right? Latent heat of melting of pure solvent by R, right? So this is basically pure solvent A, right? Or not pure solvent. In this case, we can tell this is the latent heat of melting of component A, right? And you have 1 by TA freeze, because A can have a different freezing point than B, right? You have two components, A and B. A has a different freezing point than B, and you are now looking at component A. Now, if you look at component A, you are looking at the component in pure state, right? You are basically in the phase diagram, as you have seen before. You have one axis and you have the other one. So basically, you generally use both, right? So basically, this is basically pure A side. So this is basically pure A side, and this is a pure B side. Now, if you look at that, we are looking at the pure A axis. So basically, where XB equal to 0. So that is the pure A axis. Now, in that case, you have delta HA0 melt by R and 1 by TA freeze. Say, for example, the TA freeze is somewhere here, and say TB freeze is somewhere here. That is always possible, right? So now this is pure A axis, and this is the pure B axis, right? So this is the pure, so this is your B axis, and this is your pure a-axis. Now we are saying, so if you see, we are looking at delta H is equal to melt, which is basically for pure A, the heat of transmission during melting. Heat of transmission, the positive heat of transmission during melting or latent heat of melting by R and 1 by TA freeze minus 1 by TA 0 freeze. Now for B, it will be just delta. So we are looking at B, delta is B0, right? Melt. That is the latent heat of melting with pure B, right? And you have TB freeze or TA freeze are basically the freezing point of A or B in the solution, and you have this TA0 freeze and TB0 freeze, right? TA freeze and TB freeze are that of the components A and B. Now you see, if you look at that, no solubility of A in B or B in A in solid solution. So in solid solution, XAS is 1 or XBS is 1. Basically, right, in the solid solution, XAS is 1 or XBS is also 1, right? These are pure components. So if XAS is 1 and XBS is 1, then you have this equation. And then XAL is this, right? Where TA0 freeze comes in here, because now you are now looking at XAS, which is basically XAS is basically pure, right? So ln1 minus ln XAL. So ln1 is so basically this becomes minus ln XAL. So this becomes minus ln XAL, but then this should be TA freeze minus T0 freeze. But this minus is absorbed here, right? Here, because this is 1 by TA0 freeze minus TA freeze. Similarly, you have ln XBL, which is delta is equal to melt by R, TB0 freeze, and then there is TB freeze, right? So basically, you are looking at TB0 freeze. Now see, TB freeze is like this, okay? And so basically, TB0 freeze here is what we are looking at, right? We are looking at TB0 freeze and TA0 freeze. These are the pure, right? Pure components. But we are also looking at change in B-rich solution and change in A-rich solution. But if you see, the liquid has complete solubility of A and B, right? So you have liquid which is completely soluble. So A and B are completely soluble. However, if you see the solid state, right? This is a solid state. If you look at the solid, right? This is solid. Then you see in solid there is no solution at all. In solid, there is no solution at all. It is pure A and pure B, right? So in A and B do not mix at all, right? You have pure A and pure B. And then you have also this liquid plus A and you have liquid plus B. That is why, right? You have liquid plus A and liquid plus B. And these are called liquidous lines which separates liquid plus A. There is a solid from the liquid. And you have also a very special point here where basically TA freeze, right? TA freeze, that TA freeze is equal to TB freeze, right? Basically, you can see as you go from pure B, you are coming to a mixture, you can see that your TB freeze is changing. But at this point, TB freeze and TA freeze are basically the same. TA freeze equal to, at integrated point, TA freeze equal to TB freeze equals to T, right? This is T, right? This is basically equal to TE, right? And this is a special point, or this is a special line called eutectic, right? Or eutectic point. In that eutectic point, TA freeze and TB freeze that you have in the solution, in these equations, TA freeze and TB freeze becomes equal, and that is basically the eutectic temperature. And you have XA, which is basically 1 minus XB at the eutectic temperature, and X, right? So XA and so XA is nothing but 1 minus XBE, right? So that is what is XA. So the composition of A at the composition of or the composition of the composition of the eutectic, right? The composition at E is basically XBE, right? So it is basically XB, right? And that's what we have written. XB is basically XBE, and XA is nothing but 1 minus XB solved, which is 1 minus XB, right? So at T equal to TE, as you can see here, at T equal to TE, you have liquid, it transforms to pure A and pure B. So liquid transfers to pure A and pure B, and liquid going to A plus B is a eutectic reaction, right? It's called an eutectic reaction.
but TE is the eutectic temperature and XBE is the eutectic coefficient, right? So you got one type of phase diagram. Now this phase diagram, very quickly I'll just end here. So this phase diagram can be also obtained experimentally. Say for example, if I look at this different the phase diagram, and now I look at say for example for pure B the freezing point is different, for pure A the freezing point is different, it is changing, TA freeze is changing as you go from the pure component to here, and again TB also changes like that. So TB changes this way, TA changes this way, and here somehow TA freeze happens here, TA freeze and TB freeze becomes equal, is an invariant point or a eutectic point. Right? Now, if I have to determine this phase diagram, what I can do is I basically can use a cooling curve in experimentally. So, we have A and B mixture, okay, and I have the A and B mixture in the liquid state, and we are just basically, say for example, we have pure A. So, this is pure A. So, pure A in the liquid state, and I am cooling it under a furnace, and see at 1 I am cooling under a furnace and it has del T. So, this is basically nothing but dT by dt, which is the slope of the cooling curve. The slope of the cooling curve will be different in the solid. So, if you look at the solidum or the liquidum, you will see the slopes will be different, right? Because the conductivities, the thermal conductivities are different, or thermal diffusivities. So, basically, you know this relation del T by del T. If you just look at conduction, del T by del T equals to alpha. So, alpha is assumed to be a constant, del 2T del x. And alpha is the thermal diffusivity, which is basically K by rho Cp. Now, if you look at that, K in the liquid state will be different from the conductivity in the liquid state, or density or the heat capacity of the liquid state will be different from that of the solid state. So, as a result, so basically this del T, or so we are looking at the cooling curve that we are obtaining. So, cooling curve is basically we have prescribed the cooling rate, and as a result, so basically the furnace is getting cooled. So, as I told you, this is an experimental technique, this cooling curve technique. Now, as soon as you reach the temperature here at this temperature, you see our liquid solid coexistence, and then again it falls, and this fall again is proportional to the conductivity of the thermal conductivity of the solid, right, which will be different from that of the liquid. So, their slopes will be different. But in 2, there is something very interesting that is happening. In 2, what is happening is furnace cooling is happening. The furnace cooling means the furnace is expelling it outside, right? Furnace is expelling it outside. However, in 2, what's happening is, although the furnace is expelling heat outside, there is some heat evolved, right? Heat evolved when heat absorbed, right? There is a heat absorbed. So, if you are looking from this to this, so here the heat is evolved. So, if you are looking from, so that's what we are looking at, right? We are looking at cooling curve, right? We are looking at cooling curve. So, as a result, when this transformation takes place, right? This stage, the part 2 for A is here. When the transformation takes place, it becomes basically a flat or horizontal region, right? It does not change, right? Because in this region you are basically releasing latent heat, right? Now you look at 1. In 1 there is no such thing. Since it is there, so you are if you're looking at this composition in 1, so you are now looking at this cooling curve. So you have one slope here. Now you hits here, and now you have another slope that starts, and this is basically because there is a position of A. Right, and then again 3. When you come to 3, basically you are going to here. So basically in this case, you have like again the slope change, and this guy goes down. But see, before it does so, you have 1. So basically, if you look at this, you have 1, and then you have 2. But then there is a 3, and 3 is where liquid is transformed to solid. See, in this case, when liquid gets pure liquid, now there is some nucleation that is happening, but now once you go here, you have liquid to solid transformation, right? Here you do not have liquid to solid transformation, right? You have some A nucleating inside the liquid, right? But as soon as you come here, you have liquid to solid transformation. So here again, you will have a if it is a liquid to solid transformation, you have a evolution of it, and you see that for 1 you have this horizontal, right? Similarly for E, if you look at E, so if at E it is continuously reducing, right? In the liquid state it is reducing. Now as soon as you reach 2, you are basically giving up, right? You are basically giving up heat, right? And as a result, you have this again, which is compensating for the heat that is the furnace is giving up heat, and you have some heat evolution because of this transformation from the liquid to solid, right? If this heat evolution is basically now balancing the heat released by the furnace during cooling, right? Heat released by the furnace during cooling is now balanced by the heat that is involved, right, as a process of this eutectic freezing, right, at E, right? So, and that is why you get this horizontal line 3, and then once you just cross the eutectic point, again you open up dots in accordance with the conductivity of the solid, like entire solids, right, entire solid mixture. So basically here also you can see that, right, there is this 3. So here you have 3 and 4 because there is also a 2 here, right, but here there is no 2. So if you look at this part, there is a 2 here, right, there is some change, but the change here is not liquid to solid transformation. The change here is that from here, if I go here, what we see is the nuclei of A, solid A, start nucleating inside the liquid, right? So this is for component E. Now for 2 it will be very similar, as 1, so you have 2. Obviously it will be slightly different. Why it is like different, slopes are different? Because you have a very different composition here. You have a very different composition with very different properties, right? But as you can see, for 2 also, from here to here, you have a slope change, right? Right? And then you have 3. Again, the 3 comes here, right? And then it goes to 4. Now, in the case of pure B, it is like 2 comes here, right? Because that 2 corresponds to the temperature here, right? The 2 comes. So, these horizontal lines are basically giving the temperatures. So, this cooling curve is one easy and convenient way to calculate such phase diagrams using experiments, right? You are basically making buttons of different compositions, like composition corresponding to pure A or pure B or something corresponding to 1, right? The composition corresponding to point 1 and composition corresponding to point 2, and you are melting them, and once you have the melt in a crucible, you are just allowing the melt to freeze at a given cooling rate, right? At a given as the furnace is getting cooled down, right? Furnace is giving out the heat, and only during the transformations that take place, you have this evolution of heat which compensates for this drop in temperature, and as a result, you basically get all these changes, and these changes can be plotted, and you get back basically this change corresponds to this line, right? This line corresponds to the change, right? You can see for different compositions you have these points, that you get this point, you get this point, and this point, and this and this. So if you have these changes, so immediately you can see, but only thing for pure A there is no such change, right? Pure A you have liquid, then it just goes to solid, right? For pure A you see only one slope here, right? And this here gives you the melting point of pure A, right, or freezing point of pure A. Similarly for pure B you see only one horizontal change here. So that is what I'll talk about. So in the next lecture we will talk about another type of a phase diagram where you have infinite solubilities in both liquid and solid state. So here you have zero solubility in the solid state, right? A and B remains as A and B. So XA equal to 1 and XB equal to 1, and right, A and B remains as exactly as pure A and B, but liquid has infinite solubility, right, of A and B. But here we are looking at infinite solubilities in both liquid and solid state, which is basically, and in such cases the components are isomorphous, that is they have the same structure. For example, one of the example of this type of diagrams is basically copper nickel diagram, a classic example, right? Copper nickel, both are isomorphous, they are basically having the same FCC structure, and they form a complete liquid solution and complete solid solution across the entire composition range from 0 to 1. So I will talk about this in the next lecture.